Alright guys, welcome back. So this video is going to be covering something called the kinetic versus thermodynamic product. Alright, so this is going to deal back to when we were talking about these conjugated dienes. So something like this. Oh, alright. So when we're going to be dealing with compounds like this. So before we even get started, what I want to do is I want to review one reaction you guys learned from Orgo 1. Alright. Now, I do highly recommend that before your exam, at least on your index card, is to write a lot of the previous reactions from Organic Chemistry 1, like the alkene addition reactions. Those can become very useful in synthesis. All right, and definitely review them beforehand. So what I want to do is I just want to review this reaction. All right, what will be the product and the mechanism of this sort of reaction? So we have this alkene and HBr, which is the strong acid. So if you want to pause the video and take your time to figure it out, do so now. So first step is this double bond grabs the H. This bond breaks and goes to the Br. Right? And so what's going to happen is that hydrogen we took is going to add to one of the carbons of the double bond. And it's going to generate a carbocation on the other carbon. Now remember, we always want to generate the most stable carbocation. So now it's a choice between this carbon and this carbon. We're going to pick the middle one because it's more substituted. All right. And so that H that we added, so I'm going to just change it to look blue. Right. That H I'm going to just put up here. And actually, let me move this over and fix this. So here's this hydrogen. And remember, the other hydrogens are there that were existing on that carbon before, but I'm just focusing on that hydrogen. We also have this Br minus now, which attacks that carbocation. And we get this product. All right, so hopefully that wasn't too bad. Hopefully you guys still remember that reaction. All right, and so now what we're going to do is we're going to move on to the new stuff. And so for this, I'm going to be drawing an energy diagram because it is very useful in understanding this, and you should understand how the energy diagram works. All right, and actually, let me make this bigger. All right, and so the axis over here is going to be energy. All right, and so again, remember how I said we're going to be dealing with diene. All right, and this is the reaction progress. So as we move to the right, the reaction is just continuing. So here's our diene, and here's the little spot for it on the energy diagram. And let me make this blue. All right, so that's its spot on the energy diagram. We're going to react it with HBr. All right, so again, first step is this double bond is going to grab the H. Now in this case, the double bonds are identical, so it doesn't matter which one does it, right? So these are going to be the first steps in our reaction. And so what's going to happen is the reaction is going to continue. Remember, it's going to get this sort of transition state, which is this point of high energy, and it's going to have an intermediate. Now in our intermediate, it's going to look like this. This double bond was left untouched. Now, where do we want to put the carbocation? Do we want to put the carbocation there? Or do we want to put the carbocation here? Now, remember, in terms of carbocation stability, this is secondary, so it's more stable than this primary. In addition to that, this isn't just a regular secondary carbocation right here. This is allylic. I can resonate this double bond over and put the carbocation here. So the carbocation here is much more stable than our primary. So our intermediate is going to look like this. And this hydrogen, and let's color that hydrogen in green, just so we keep track of it. There he is. All right, so that's our intermediate. Now what I do want to show is I'm going to show the resonance on this energy diagram. So this intermediate can resonate the double bond here, like we just discussed, moving the carbocation over this way. Let me fix that. And here is our hydrogen. All right, and so keep this resonance in mind. Now we still have our Br minus. All right, so he's going to attack our carbocation, and so I'm going to just pick this guy. I'm going to focus on that intermediate right now. All right, so what's going to be the product of it attacking that carbon? All right, so let me go back to blue. So let's draw our energy diagram here. And so what's going to happen is a double bond is here, our bromine is here, and that hydrogen that we added just to keep track is over there. Now what if it attacked this intermediate right there? All right, so here's our bromine. Let's draw another one. Now it's going to attack that carbocation. So before I even draw the lines on the energy diagram, let's just draw that product. The double bond is now here. Our bromine is going to come off of here. And our hydrogen is still there. All right. So what I want to do is I want to look at both of these products right here. All right. Look at this double bond. It's at the end, right? So there's two hydrogens coming. There's a carbon, right? Or it always has to be a carbon there. Carbon with two hydrogens. And then this carbon right here is bound to one carbon. If we look at the double bond at our product over here, this carbon is bound to one carbon, right? This one over there. And then this carbon of the double bond is bound to that carbon. So he's bound to more carbon. He's more substituted. He has a more substituted double bond. So he is more stable. So this product, where we have the more substituted double bond, is the more stable product. This is the kind of product, this product we're going to call the thermodynamic product. This guy up here has the less stable double bond. All right, so he's the less stable double bond, but if we look at our intermediates, think of it this way. This intermediate forms, then to form the other resonance structure, we have to resonate. But this one forms faster because I don't have to resonate to get to it. I just take the H and the carbocation, boom, right there. Whereas to get this guy, you gotta move your double bond around. So he forms faster. So the Br minus will attack that one faster. Therefore, we call this guy the kinetic product. All right, so the kinetic product is less stable, but he forms faster. And now when we say he's less stable, we mean he has higher energy. And so what's going to happen is if we were going to draw the energy diagrams for our thermodynamic product, it's going to look like this. And I'll change the color in this case and draw it purple. Higher energy. But more stable because he's lower down. All right, so that's the thing to understand, that the thermodynamic product will have lower energy overall than the kinetic product, but if you look, he has a higher activation energy. It takes more energy to form it. And so to form the kinetic product, usually we have it at lower temperatures. All right, lower temperatures. This guy forms faster. The thermodynamic product, he forms at higher temperatures because more temperature, the hotter we are, the more energy we can pump in. Forms slower. So when we do these reactions, we can get mixtures, but if we change the temperature, we can get one as a major product. All right, so sometimes in the questions they'll ask you to draw both the kinetic and thermodynamic, or they'll ask you to draw just the thermodynamic, or they'll just give you they'll say hot, and they'll expect you to understand that, okay, they want the thermodynamic. All right, and so what are we going to do now, right? So we have to figure out how to draw these, or how to determine these, right? Because it's not always going to be as simple as this example. Now, also one thing you guys may hear, the thermodynamic product is sometimes called the 1,4 product, 1,4 addition. Just wanted to bring that up in case you guys hear that. And also kinetic is going to be 1,2 addition. Not always, but sometimes. All right. And so the reason it's called 1,2 and 1,4, if we look at the placement of the Br and the hydrogen, label this is 1, this is 2. You could have done this one as 1, that's 2. Thermodynamic, 1, 2, 3, 4. And if you wanted to do the reverse, 1, 2, 3, 4. All right. So let's go through an example, and it's going to help us figure out how to answer these sort of questions. So we have this 5-membered ring. All right. And all of these examples are going to have these little like dynes. All right. This is the primary focus of this. And we're going to react with HBr. Now this is a multiple choice. It said select the 2 major products of the following HBr addition. They didn't give us a temperature, so we assumed they're asking about the thermodynamic and kinetic, plus they said 2 products. Now this was given as a multiple choice, but it could easily have been a short answer, so we're going to take it as a short answer. All right. So there's a stepwise procedure we can use to answer these questions. What we're going to do is we're going to look at each double bond one at a time. So let's start with this guy first. So what I'm going to do is this guy is going to grab the H. This Br breaks off. So we're going to get this. This double bond stayed the same. We have this. Now here's our dilemma. We can form the carbocation here or here. How do we decide which is which one we're picking? Remember how we were able to resonate this guy here? We need to be able to do that. So if we picked to form the carbocation here, this double bond is now too far away to resonate it. If I put the carbocation there, I can resonate this double bond over and shift the carbocation. This must happen. You always need this, all right? So whenever you're figuring out the carbocation and where to put it, you want to put it in the position of resonance. So if you're looking at the dyne, it's usually the carbocations that are, the carbons of the double bonds that are closest to each other, right? So when you pick the double bond that you're protonating, right, usually you want to pick the carbon to form the carbocation that's closer to the other double bond. So we're picking that double bond, right? So this guy is secondary allylic. Now what we're going to do is, before we do anything else, we're going to do it with the other double bond. So redraw. Now obviously you're not going to have to go through this exact procedure every time, but this is just to help you learn the idea. We have our HBr. Now let's use the other double bond, grabs the H, breaks it off to the Br. And so what are we going to get now? Remember, we want to form the carbocation so it can still resonate. This double bond remains the same. So our 2 possible positions of putting the carbocation are here or here. So if I put it there, remember I can't resonate this guy because that carbocation and double bond are too far away from each other. So I'm going to put it right here on the carbon closest to the other double bond. All right, so that's going to be our carbocation. Again, this is just a secondary allylic. So what you can do is we're going to look at the resonance structures now of these guys, and what I'm going to do is I'm going to separate them a little bit further so we have some space. So I can resonate this guy this way, and I'm going to get this structure. Carbocation now moves this way. And now to look at this guy, resonate this guy over now, that double bond. Yeah, that was too close. Double bond moves there. Carbocation now over there. So our original structures were both secondary allylic, And when I resonated, now this carbocation is on a triple bond, a tri-substituted carbon. It's got 3 substituents, and it's allylic. So tertiary allylic. And this guy, he's still secondary allylic after the resonance. All right, and so what the whole goal of what I just did is the first thing you want to always figure out is the 2 spots where we can put the carbocations where they resonate. After that, you need to figure out of those 2 carbocations, which one will give me the more stable carbocation. So when dealing with the dienes, the 2 spots where we can put the carbocation so they can resonate are always the 2 closer ones. This one and this one. Once we figure that out, you now have to look to see which one of those, if I put the carbocation at one spot and at the other, when I look at resonance, all right, so I put this look at resonance. All right, so first step, find carbocations, which I'm going to do is C+, find carbocation positions where we can resonate. That's step 1. Step 2, we're going to need to find, so looking, or actually using resonance, find the most stable carbocation. All right. So in this case, originally, so we found our 2 structures where the carbocations can resonate. The original structures were this guy and this guy, both secondary allylic. What we now do is every time you have to look at resonance, and you see that we created a tertiary allylic, and this guy stayed secondary allylic. So we found that putting the carbocation here, where we did, is the best position. Sometimes you'll get lucky and you're already at the most stable position, but always look at resonance to confirm. So what we're going to do is we're going to now look at this and only these pathways. Once we figure this out, you can cross everything else out. All right. So I'm actually just going to erase these rules here. You guys can always go back. So these are our important structures. All right. So these 2 resonance structures, one of them will help us find the kinetic, the other one will help us find the thermodynamic product. So let's erase this arrow. So remember, the kinetic product is going to be the one that has the least substituted double bond, right? Not the most stable carbocation. It doesn't have to be anything in terms of carbocations. We need to figure out the one with the double bond. So you look at this guy and this guy. Where's the double bond more substituted? So looking at these 2 carbons and these 2. So for the one on the left, he's bound to 1, 2, 3 total carbons, and on the right, he's bound to 1, 2. So the one on the left has the more stable carbocation. Sorry, more stable double bond. So our Br minus now comes in, attacks, and our final product is going to be this. Br, let's move this, and the methyl. In this case, we're going to have the Br attack, that carbocation, generating this product. Double bond up here now. All right, and so the more stable double bond will be our thermodynamic product. The least stable double bond will be the kinetic product. Right, and that's how we would go about this kinetic versus thermodynamic. Now, one thing to keep in mind, when dealing with the theory behind this whole thing, another reason I wanted to bring up the energy diagram is because a lot of times they will ask you a question specifically targeting the theory of kinetic versus thermodynamic. All right. And so one key thing that you guys should know is that this, while I showed you the resonance structures here, when dealing with the actual theory behind it, what you should know is that this reaction, when dealing with kinetic thermodynamic, forms a single carbocation intermediate with two electrophilic sites. Right, the electrophilic sites are the two possible carbocations we form, like we did in this example, but it is considered one carbocation intermediate. That's why right here, that plateau, that is the intermediate. And you see that there is still only one line. It hasn't split off into this blue and purple yet. So there's one intermediate with two electrophilic sites. And the reaction is fastest at the site that leads to the least stable product. So reaction fastest at the site that leads to the less stable product, which is also called the kinetic product. All right, so in the next video, we'll just do some practice questions regarding kinetic versus thermodynamic, because this is hopefully something that you can get easy points on. All right, and as always, just the more practice you get with it, the better you will be at it. Hope this video helps, and I'll see you in the next one.